Awesome. Well, I'm really excited to be here with you today. And yeah, shocking, this is actually a talk by me that is not about Zio. But don't worry, we'll still find a way to work some Zio in there. But today I'm here to talk to you about something we've been working on at Zyverge over the last 6 months or so. And it's a solution for this problem of durable computing. So what I want to do today is start by talking to you about just what is durable computing? What are we talking about when we talk about this problem? Then I want to talk about why we should care about that problem, why this actually matters to us. And then we're going to look at different solutions to that problem. First at the application level, then at the framework level, and then spend some time thinking about what the future could look like for really solving this problem in the nicest way possible. So what are we talking about when we say durable computing? The way I define durable computing for you is a program is executed durably if transient failures of the hardware that it's run on don't impact the externally observable semantics of your program. So a couple things to note there. One is it's about where your program is executed. So it's not just about your program itself, but it's about how your program is executed. And it's about the externally observable behavior of your program. So clearly, if this computer just doesn't work and something's running on there, something just different is going to happen, but that difference in behavior isn't observable to the stakeholders who are interacting with your program or your business, your application. So to take a simple example of this, I've got a little e-commerce workflow here. And I've written it as a for comprehension with Scala 3, with all of our braceless syntax here. And it's pretty straightforward, right? We need to reserve some inventory to make sure we actually have this thing. And then if we have it, we need to charge the customer's credit card. And OK, if they actually have the money for us, then we need to say, OK, we got a successful order, and we got to create a shipping tracking ID, and we got to actually give them their product and do all this stuff. And a really important property of this program is we've got to do each of these things exactly once. Right? If we charge the customer's credit card and we never send the product, we're going to get some kind of complaint from them, and whatever regulatory agency is in the country we're in is going to be coming after us. And likewise, if we charge the customer's credit card twice, even though we sent the product, that's not going to be good. So we need to do each of these things exactly once. And that's exactly what durable computing gives us, is if we're running this in the cloud somewhere and gets redeployed by Kubernetes, this server it's running on goes down, we pick up exactly where we left off, and we keep going, we do each of these things exactly once. So that's what we mean when we say durable computing. And as I mentioned before, durable computing is a property of program execution and the environment a program is executed on, and not just the program itself. So if I have any program and I run it just on my computer and I dump some Coke on it, that program is not going to be executed durably. It doesn't matter what code I have, what I'm using there. So it's a property not just of the program, but about the environment that the program is executed in. And we'll come back to that later, and we'll see this idea that you need an environment to execute it. Maybe only some subsets of programs be executed durably, or maybe actually all programs can be executed durably with some environments. So what would it mean to execute a program durably? Like, it's a little bit weird, right? We say, oh, I'm just going to run this program on my computer, I'm going to dump Diet Coke on it, and my program is still going to run. Like, how is that going to happen? And so conceptually, I think we can say there are probably 5 things that we need to happen to execute a program durably. So the first thing is we have to be able to detect that a failure occurred, right? We have to detect that we're running on my computer or some server, and that computer blew up when it was doing something. And we can imagine we've got ways of doing that, right? We've got Kubernetes, we've got health checks. There are ways that we could see that something isn't working anymore. Then we take that program, and we need to run it somewhere else that has not blown up. OK, fair enough. Again, we've got things like Kubernetes that are going to do that for us. Then we also need some concept of where were we when the failure occurred, right? So we had that set of 5 steps. We need to know I was after charging the credit card, but before storing the successful order, or I'm kind of SOL in any attempt to recover from this thing. And then I need to have a way to restore the state to where I was immediately before I blew up. So you can imagine my example is very simple, where I just said do these 5 steps. But maybe in my first step, I get some kind of confirmation number that I need to include in the 4th step, that I need to include that in the information I'm sending to the customer. So I need to be able to restore all of that state. And then finally, I can continue on my new machine with whatever I'm doing. So all the solutions we're looking at, we can look at them through this kind of framework of how are they helping us do these 5 things, and particularly these last 3 things, because the first 2 are kind of easier. We have tools for them. The last 3, not so much. So what makes this hard? Well, the first thing that makes it challenging is that failure can occur at any point. And so we have to think about this throughout our program. And this is a little bit where that Zio analogy maybe comes in, of if you've programmed with Zio, you're used to this idea that interruption can occur at basically any point. And so we have these specialized operators of acquire, release, and uninterruptible to make sure that we don't get interrupted in places that we really don't want to get interrupted. But in this case, it can both occur at any point, and there is no uninterruptible operator, right? There is no infallible operator that my hardware is not allowed to fail in this code because it's particularly important. The second thing that makes it hard is that the state of our program can be very complex. So in English, it's kind of easy to say, well, there are these 5 steps, and I need to know I did step 2, and I haven't done step 3 yet. But when you actually take that into code, even that like simple 5-line program, my actual state when I'm 2 lines into that is this giant lambda of Zio continuations and functions that are doing the next thing, and maybe capturing over variables, and maybe having a call stack. So all of those are things that we need to restore if we want to be able to continue our program. And finally, we want to do this in a way that is performant and ergonomic. Of ideally, we want our program at the end of the day to look as nice as that original program and to still be fast so we can serve lots of these e-commerce orders and be responsive to our customers and all this stuff. So we have some challenges here. Beyond what we talked about, why does this matter? Well, one of the ways I kind of like to think about this is that right now we're having to all be distributed programmers because of these issues, right? We're pushing more and more work to the cloud, and we want to scale out. We've got just more and more spending shifting to the cloud. And basically all of this is running on this commodity hardware that can fail, that can be updated, that can be redeployed at any point in time. And so the possibility of failure is no longer kind of, oh, this is an unusual thing, this is someone else's problem. It's, no, this is an expected condition, this is my problem. It's kind of like if you went to Eric's talk yesterday about Kafka, and he talked about his issues of switching threads. Well, switching threads is just, that's the nature of the reality. Like, you can't blame someone else for that. That's a problem you've got to solve. And so all of us are being put in the position of, we have to create durable execution just for our programs to be correct, right? Just to have that e-commerce workflow running on the cloud somewhere and have it do what we want it to do, what we need it to do. We've got to solve durable execution one way. And it's not a question of kind of do we need it or not. It's just a question of how we're going to solve it. And I think a useful analogy here is going back to asynchronous programming. So if you think about asynchronous programming, we had a similar big technology and business change, right? In that case, it was multi-cores, right? We had just a shift in technology development where basically Moore's law went from being just more on the same core to more cores. We had a business need of we wanted to just continue doing more. And so what that meant for all of us as developers is that we all had to become asynchronous and concurrent programmers. And we were all doing this stuff initially basically with callbacks, right? That was like the application level solution of handling this. So if we say, okay, we got all these different cores, we need to do things with them, we need to use threads, we need to use callbacks, we need to have atomic variables and all these things. And then eventually, what we got instead of that is we started to build frameworks on top of that that made life easier for us, that said, you don't have to solve these problems yourself. The framework is going to solve more of them for you. And you can really think about that's where Zio sits, of we have this problem of asynchronous and concurrent programming. let's handle more of it at that ZO level so we don't have to ourselves. And right, you see a lot of this of like, you still use the threads and you still use the callbacks internally in ZO, but it all gets wrapped up there. And so when you're at the ZO level, you just do for each par, and everything gets run in parallel. And if one of them fails, the others get interrupted, and everything works just the way we want it to. And so I think we could ask ourselves, what is this evolution going to look like for this durable computing evolution? What are we doing right now to solve this, right? What's kind of the equivalent of callbacks that we're using today? What would a framework look like that actually addressed that? And what could be the ZO of durable execution? So let's first look at what an application-level durable computing solution would look like. And that's basically event sourcing, right? That's kind of the way that we approach this problem if we're trying to solve it ourselves, is we move to an event sourcing framework, we use something like maybe Kafka to do this. And we had that talk yesterday about ZO Kafka for this. And so the idea would be that instead of operating on just the state of our program, we now operate in terms of events. And so we think, well, we don't have just like a shopping cart. We have a set of events of, we have an add something to the shopping cart and remove and update. And the state at any time is not an actual thing. It's just this like aggregation over this event stream. And then we have this like append-only log of, OK, we have all the messages. And that kind of gives us the tools to solve this problem in at least one way. Because if we go back to kind of our set of things we need to solve, we say, OK, we had a failure occurs. Where were we when the failure occurred? Well, we just look at the log, right? And we say, everything that's in the log is something that we know was completed. And everything that was in the log, for our purposes, was basically never done. And we just pick up where we left off in the log. And similarly, if we say, well, how do we restore the program state to where we were before failure occurred? Well, we just take everything in the log up to that point, and then we have our new state. And we can do some tricks there to make that a little bit nicer, but that's basically our approach. And we also accept some things there, right? We say, well, right, I said for our purposes, anything that's not in that log never happened. Well, that's maybe not entirely true, right? Because maybe failure occurred while we were processing one of those, kind of the next thing that would have gone in the log. And so we accept that as far as each of those messages, it may actually be retried, processing one of those steps if it didn't make it into the log. And we saw that a little bit yesterday with that Kafka talk about what happens if you have a failure of rebalancing. And you have a bunch of issues to solve there. So what's nice about that approach? What are the good things to that we want to kind of keep? Well, I think one is it's very battle tested, right? Like lots of people do this. It's used by lots of places. There's lots of things we can read about it. If you're doing it, you're doing some variation of this. So there's something to be said for that. Another thing that I think is nice about this is that there's no magic to it, right? It's very clear about what you get and what you don't get. And we've even just talked right now about some of the guarantees you don't get from this. And I think the other thing that is nice about this is you can think about it as being a foundation. So just like when we're talking about asynchronous and concurrent programming, and we said, well, callbacks, we don't want to use callbacks ourselves, but callbacks are used all the time internally in ZO. Threads are used internally all the time in ZO. So it's not necessarily that we can or want to get away from these things, but that we want to put them in the right place. We want one thing to handle them and for us to not have to handle them ourselves. So what are some of the disadvantages of event sourcing? Why is this not just the perfect solution for us? Well, I think one word I keep coming back to is this concept of being invasive. And so you could think of this as how much do we need to change our code to achieve something, right? If we need to change our code a lot, it's very invasive. It gets everywhere into what we're doing. Versus if it wasn't invasive at all, we would just do exactly the same thing we were already doing. So event sourcing ends up being pretty invasive, right? It becomes essentially a whole application paradigm. It's in a way a little bit like Zio or actors. It's kind of an idea of this is how you should architect your entire application, which is totally fine and can be a good way to architect your application. But I mean, one, it's different if that's not the way you were doing it before. And two, I think if you step back, you'd say it's probably not the most natural way to think about a lot of problems, right? If you just asked me to conceptualize a shopping cart, I would kind of say, well, there's this thing, and you put things in it, right? And you say, oh, I've got a shopping cart that has 5 things in it. You don't say, oh, well, I've got an event stream of everything that historically happened to the shopping cart, and the shopping cart is the aggregation of the event stream. That's like a very abstracted way of thinking about it that you probably only get to if you kind of needed to get to for this particular problem. Another issue is that it ends up being relatively low level. So once you have something like this, then in addition to kind of the overall just framework of event sourcing, then you need some tools and libraries to help you with it, whether it's Kafka or something else like that. And then there's a bunch of other stuff you have to figure out of just how you're using that, right? And in our Zio world, if you're using Kafka, you're going to use Zio Kafka, and you're going to use Zio Streams, and then you're going to want to watch Eric's talk from yesterday and hear about all of these issues with Zio Kafka and how they're working through them, and you're going to want to manage these streams, and you're going to want to figure out, well, when do you want to aggregate them so that you do the commits at the right point, and how frequently should you do that, and how much do you want to group things, and there's a lot you need to think about with just that I mean, again, before you got to thinking of this, you just wanted to have a shopping cart, right? You just wanted to have your little e-commerce application or whatever it was that you were doing. And I think the final thing is just you end up mixing concerns there, right? Of your logic is kind of a combination of your core business logic and this durability logic, which ideally we like to be very separated, right? We'd like to just have our business logic and have that totally different than how we're handling durability or concurrency or all these other things. So OK, that's kind of the application level solution. We say, all right, we don't want the application level solution. We want something that's more like a framework that's going to help us with this, right? That's what we liked about Zio. So let's see what that looks like. Well, we tried that. We had this thing called Zio Flow. And I don't know if anyone remembers this from previous functional Scala conferences. We actually had a bunch of talks about this. But we had this whole library called Zio Flow, and its core data type was this thing called a Z-flow. And so if you see the REA, it's probably looking a little bit familiar. And this was basically a data type that represented a durable workflow that could require an environment R and succeed with either a value A or fail with an error E. See, we're getting back to some of the Zio stuff here. And it came with a durable executor that would make sure that when you ran one of these Zio flows, if you ran it with this executor, that it would, even if a failure occurred, it would get restarted and it would pick up from where it left off. So it had these nice properties that we like here. And so what this would look like is basically we would have exactly the same for comprehension as we had before, except now all these lines here, all these lines here would be Z-flows instead of Zios. And so there's definitely something nice about this, right? That it looks very much the same. So if we compare it to like that event sourcing paradigm where we really needed to kind of think about things in a completely different way, now we're thinking about things in a more similar way. So OK, great. And how does this Zio flow work under the hood? Well, it's very similar to Zio. So each of these Z flows is a description of one of these workflows, but these are now descriptions that can be safely serialized, and they make sure that everything that they capture can be safely serialized so that we can replay their state at any point in time. And in addition to that, we have this concept of an activity. And so an activity is basically an interaction with the external world. And so when you execute one of these ZOFlow programs, what it can do is before and after you have these interactions with the external world, it can save all of that state as well as at regular intervals. And then if a failure ever occurs, it just brings back that state, and it carries on from just where it left off. And this includes the stack, all these variables, because all of this is written in this ZOFlow language. So what's nice about this? Well, it's definitely less invasive. Right? We saw that the architecture of our application didn't really have to change, that we still had that same for comprehension, we still had those same 5 steps, we saw them one after another. So that's nice. At the same time, we do need to change every one of those type signatures to be a ZFlow versus ZO. And those are similar data types. They have similar operators, but they don't have exactly the same operators. So still something there. It's definitely higher level, right? If we think about like worrying about those details of how we were consuming the Kafka streams and all that stuff, we don't really have that anymore. Maybe we plug in at the configuration level. Are we using Cassandra behind the scenes? Are we using RustDB? What are we using? Maybe we have some knobs we can tweak, but we've pushed that to the level of configuration versus all these different issues when you think about it. And we definitely have more of a separation of concerns of now we really are just saying what we want to do, and we're leaving it to kind of this ZOFlow execution engine to execute these things durably. So definitely good things there. But why is this still not the greatest thing? Why is the end of the talk not ZOFlow? So the first one is it's still relatively invasive, right? We just said you have to use this ZFlow data type everywhere. So if you originally wrote your program with ZO and you're doing all these things, now every one of those type signatures needs to change. And you need to use this concept of activities, and there's a concept of remote variables instead of normal variables. So there's kind of a whole set of things there. And that's kind of the best case, right? Because that's assuming you're already using ZO, which I love ZO, everyone should use ZO, but the reality is there are lots of people who are not using ZO, maybe not even using Scala, right? I mean, as much as we love Scala here, there are hundreds of us at this conference, and we could go to other conferences for other programming topics where there would be thousands of people, or even more than that. So we're still kind of saying you need to come to us versus we're going to go to you to solve this problem. It's definitely experimental, right? I have people ask me about ZOFlow, and I was like, look, it's an early stage library. It's looking for contributors. It's looking for early adopters. So definitely, if you're interested in this, reach out. But definitely in the early stages. And there's some performance cost for all of this. Of essentially what we're doing with this ZOFlow approach is we're writing a language, this ZOFlow language, that compiles down to the ZO language, that then compiles down to the Scala language, that then gets compiled to bytecode like all of our normal languages. And so there's a cost to those different levels of compilation. And over time, I'm sure we could optimize that and get that to be lower, but there is a cost there. OK, so where are we going? How can we do better than that? Well, I think a starting point is how could we completely eliminate the need to rewrite your code, right? So I talked about that concept of being invasive. And what if we took that to its logical extreme and said to be not invasive at all would mean you do not have to rewrite your code at all. So you can give me any program you want to. And as long as you hand it over to me, I can take it and I can run it durably. That seems like that would be a pretty cool property to have, right? This problem just gets solved for you. You don't have to do anything different with your code. You don't have to do refactorings. You don't have to learn a new framework. You just give me your code and I will execute it durably. OK, I mean, sounds good, right? Lots of things sound good. I'd also like to have $1 billion. How would we actually go about doing this thing? Well, I think to do that, we got to think about the right language. And so with ZO Flow, we got to create our own language. And so we got to create whatever language we wanted that had the properties we needed. And so that's why we added all these things to it. We had this concept of these like workflows, and we had this concept of these remote variables and these activities, and we made you use that language. And as long as we made you use that language, then we could give you this property of durability. But the disadvantage of that is you have to write in our language, and no one else knows our language because we just literally invented our language. So that's not actually that helpful for people. So how could we instead find an existing language that we could use for this? And it's one of those, in a way, it's like the Goldilocks thing of, it's not too hot or too cold. In this case, it's not too high level, not too low level. Because you've got some of these languages, like Scala or Java themselves, that you could say they're too high level, or maybe you could say they're too flexible. That like, I can just do anything in the world I want to in Scala or Java. So I'm trying to execute this program durably and kind of see where I am and what's going on and save the state to replay it. But you've just randomly created some new thread that in 10 seconds is supposed to come and do something. How am I supposed to know about that? How am I supposed to just like recreate this like thread? Like, it's just, I can't do it when it's a completely unbounded domain like that. And likewise, we could say, okay, well, what if we like look way later in the compilation process and we look at the point where like you've compiled this down to bytecode, and then we kind of have the opposite problem of it's too low level of like, yes, it's very restricted. There's like a very limited set of operations there, but there's not a sane way to kind of recover the structure of like, okay, what's actually going on here and how do we transform this in a way that makes sense to add this element of durability to it. So this is where this idea of WebAssembly came in. And so as we were thinking of this problem and we were looking at what existed out there in the world, we noticed that WebAssembly is something that kind of independent of Scala, independent of durability, independent of all this, was just growing in importance as a compilation target. And WebAssembly is basically a compilation target kind of designed for the web. That's where web in the WebAssembly came from. And you can compile to WebAssembly from a variety of different languages. And you can run the server, you can run it in the client. But one of the motivating factors for kind of development of WebAssembly was this idea of its security model. Because the idea is this might be some program that's like running in my browser that like it's come from whoever. And you want to have a very strong set of guarantees that this program I'm now running on my computer is not just going to like download my entire file system and like send it to some server with like hackers in some crazy place. And so there's this execution model, it's called sandbox execution model, where essentially a WebAssembly program can only interact with the external world through capabilities that are provided to it. So anything you want to do, basically, other than like math or manipulating collections, has to come through this set of capabilities. So I want to print to the console. That's a capability that has to be provided to my program. I want to generate a random number. That's a capability that has to be provided to my program. I want to make an HTTP connection. I want to work with a socket. Those are all capabilities that have to be provided to my program. And that's actually exactly what we need to address this durability problem. Because what it means is that when we go to run one of these WebAssembly programs, we can provide our own versions of every one of these capabilities. And our versions can essentially leverage all of those techniques of event sourcing that we were talking about before. So all those versions, all those capabilities can capture everything that your program does and record it in our version of an operations log. Right? Think about that like append-only log from event sourcing. And we can do things on top of that with snapshotting and things like that. But that's kind of the core idea there of, imagine you have a program and you make an HTTP call. Well, because of this capability model, we can know, hey, you made this HTTP call, and here's exactly what you got back. And we can keep track of all that stuff, and we can use a lot of those same techniques, but again, we're using it internally now versus you having to use it at the user level. And so that's exactly what we've done with the product we're developing that we call Golem. And so Golem is our execution environment that supports durable execution for any program that can be compiled to WebAssembly. So again, like that dream of like the non-invasive solution for durability. If you give me any program, as long as you can compile it to WebAssembly, I will give you back a durable version of that program that I can run in this Golem execution environment that will do all those things we talked about, that will run your program, will scale it out if necessary. If it fails, we'll detect that failure, we'll restart it on another node, and we'll pick it back up from exactly where it left off without you having to write your program differently. We have that log of operations, know exactly where the failure occurred, and we can restore that state either by using that log if necessary or by snapshotting the state after we got to a certain point with that log. OK, that all sounds good. Now, there's a little caveat here, right? This like compiling to WebAssembly. So the WebAssembly ecosystem is rapidly evolving. I think as with all exciting things, it's in the process of becoming. And so some languages have really good support for it. Rust has excellent support for it. Some languages have getting better, right? Like it's support, you can do it with Go, you can do it with Python. There are already a lot of compilation targets for it. But right now, Scala does not have support for WebAssembly. But we know that JavaScript does have support for WebAssembly. There are some caveats there that we'll get to. But as of a few months ago, there's a thing called componentized JS that will take a JavaScript program and compile it to WebAssembly. And what did we learn yesterday in one of our talks about how great cross-platform support is? Well, we heard how we can go from Scala to JavaScript with Scala.js. So if I kind of put the arrows in the graph together, I should be able to go from Scala to JavaScript with Scala.js. And then with this componentized JS thing, I should be able to go from JavaScript to WebAssembly. And so if I do those things, then theoretically, I should be able to run a Scala program with Golem. Let's see what it looks like. All right, can folks see? Yep. All right, excellent. And yeah, I think size good for everyone. Thumbs up. All right. So what I've got here is a very simple Scala program here. And you may notice a couple different things. So let's kind of walk through them. So I'm starting us off here with this thing called a WIT file. And a WIT file, the way I would think about it is it's like the protobuf file for this WebAssembly ecosystem. So again, if we go back to yesterday, we had our talks by 2 of our 3 Daniel speakers yesterday. And someone was arguing for a code-first approach. Someone was, maybe arguing is too strong a word, but someone has solution for a code-first approach. Someone has solution for a spec-first approach. This right now is taking a little more of a spec-first approach. Ultimately, you should be able to do both with this WebAssembly ecosystem, but right now, at least what I'm showing you right now is a little bit more of a spec-first approach. And so we've got this thing called a WIT file, which again I would think of as like a protobuf file, that's basically just defining an interface, in this case for our shopping cart here. And so these are the methods on our interface. And so we can do basic shopping cart type things, like we can initialize the cart, and we can add items to it, and we can remove items, and we can get the contents. And in particular, you may notice here that in addition to having simple types like strings, we can have user-defined data types like this product item. And if we scroll up here, we can kind of see these things. And again, it's very protobuf-like of we have records and we have enumerations. And so this product item is just basically an equivalent of a Scala case class that has some strings and some doubles and ints inside of it. But this essentially defines the specification, the interface for our shopping cart here. And so what I'm going to do now, and where kind of the new stuff starts out, you could say, is I'm going to run this wit bindgen command. And this is very much inspired by Rust and the support that Rust has for working with WebAssembly and the particular component model with cargo. But if we go in here, let's see if I can actually, well, here, let's see. So what this has done is this has now generated a Scala file based on that wit file here that I'm now able to depend on in my Scala code here. So now I have this shopping cart that is extending this API trait, and this API trait has been generated for me based on that wit file and has method signatures that reflect all of those methods in my specification. And now I'm just going to implement them here, and this is just normal Scala code, right? If I put some nonsense in here and I compile this is not going to compile. So all of this is like being compiled, being type checked, all this stuff. And I'm doing very simple things here, right? I can just use normal Scala code. I think the only things that are not completely vanilla Scala is I'm just using these two annotations here from Scala.js. We're working on getting rid of those. But essentially, all I have here is I have this state, which is basically just a normal case class with some methods on it. And every time I do one of these things, I'm just updating that state. And in this case, I'm just maintaining my state as a normal variable. I could have used a ZRef or an atomic reference or something. But in this case, I'm just using a var for this. And what I can do here is I can then run another command called component. So just SBT component, basically. And what this is going to do is it's going to do both of the steps of that process. So it's going to take this, it's going to compile it to Scala.js, and then it's going to take that, and it's going to create a component based on it. And now if I just go in here, I've got this component.wasm thing, which as is not a human readable thing, but this is now a WebAssembly program that reflects my Scala program. Now, one caveat here, you may have noticed I was just doing pretty simple stuff. I was not doing any fancy ZO stuff with concurrency or asynchrony. I mentioned the WebAssembly ecosystem is rapidly evolving. One of the things that componentized JS team is working on adding support for is the JavaScript event loop. So right now, synchronous code in here, which is definitely a limitation that I think is going to be relaxed next year. But at the same time, if you can create one of these workers for each of your shopping carts, you've got a very high degree of parallels and concurrency there. Maybe you don't need it so much in processing your individual shopping cart worker. So let's now take this, and let's see what we can do with it with Golem. So I'm just navigating in my browser here to this console.golem.cloud. This is in developer preview, so it's completely free for anyone who wants to check it out. So go and log on right now and make trouble. And in particular, I'm going to go into projects here. And I've created a new project here called Functional Scala 2023, which is basically just like a folder to organize things. And I'm going to go to workers here. And I can just do create new. And I can just upload that component.wasm file that we saw a minute ago. And when I do, I'm going to get this. And this, in a way, is our proof point that we really did compile this to a valid WebAssembly worker. Now, one, just the upload would have failed if it couldn't compile to a WebAssembly worker. But two, we can actually see this method signature here. And so all of these methods are reflecting those same interfaces that we defined in that wit file. And all that goes into the WebAssembly file and is something we can introspect on and we can then present to you here. So we can look at that file and we know, like, hey, it's the shopping cart and it has these methods to initialize it that takes a user ID that's a string, to add an item that takes a record that happens to have 4 fields, and it's a product ID, it's a name, a price, and a quantity. And I think the cool thing at this point is, as far as everything else with Golem is concerned now, this is just a WebAssembly program like any other. It doesn't really matter that it came from Scala versus from Rust versus from Go versus from Python. Under the hood, it may be that the Rust-based version would run a little faster, but that's already true with your Rust versus Scala-based programs. So at this point, they're all full citizens here, and we can do everything we could do with any normal Golem program. So I can go to my workers here, and I can grab one of these. And let me call some methods on it. So it sounds like I should probably initialize my cart first. So it seems to think it's some fancy thing, but I'll just call the user ID Adam. And I'll invoke this function. And it says, OK, I've initialized my shopping cart with a user ID of Adam. Great. And then let's add something to the cart. This will be product ID 1. This will be maybe a shirt. It's $20. I just want one of it. OK. And then if I get the contents of my shopping cart, there it is. And the thing you may notice about this is there's no database. Right? So I don't need a database for this anymore necessarily. I previously needed a database because the database was what was giving me some of this durability, that like when this program stopped running, I needed to have some way to actually go and get what the quantity was for the shirt here. But if I have durability, if I really know that this program is always going to be available to me, if I can be brought up from a suspended state at any time, maybe I'll need a database for this. Maybe need it for other reasons, right? If I want to store a giant image, I should probably not do it in memory. Maybe if I want to aggregate information over all my customers for analytics, then probably don't want to just have it in a bunch of workers. But maybe this is this ephemeral shopping cart thing that like I don't really want to do anything with until someone actually checks out from their shopping cart. Maybe this is all I need. And let me show you something else cool here. So let's go back here. And so far, we've been looking at these templates. The other thing I can do is I can define APIs based on these things. So let's look at one of these. Let's see if I can edit it, or maybe I'll just create a new one. So let's call this maybe shopping cart 2 will be my little subdomain for this. And once I have one of these, I can create routes for it. So like here, let's edit this one. I'm saying anytime I get a GET request to my shopping cart domain, I'm going to capture this ID as a variable here. I want to serve that GET request by calling my shopping cart template with that worker ID. And I want to just respond back with whatever I get there. So now let's try doing that. Let's see. Actually. I think I have the wrong binding here. Hold on 1 second, just say otherwise. Oh, let's see. Did I do cart 2? I thought I did cart 1. Let's see. Maybe a different subdomain, maybe so. This is why I'm, all right, well, I will follow up on that. But let me go back here. Let's go, oops. So I think the takeaway from this is in the future, I think we're going to think about doing durability yourself at the application level a little bit like how we think about dealing with threads ourselves today. We're going to say, yeah, it's something you could do. Maybe some of us have done it at some point as a learning exercise or to do something low level, but that it's kind of not best practice because it's error prone, because there's a lot of complexities of how we're dealing with this distributed state, how we're managing this that are easy to get wrong. And I think what we'll hopefully have is more tools. Hopefully, Golem will be among them that will solve this problem for us and do a little bit like what Zio has done for asynchronous and concurrent programming. And I mean, maybe actually at a nicer level, right? Of one of the things we heard last night from Flavio was this idea that even Zio itself was like, it's pretty nice, but it might be nicer if we didn't have to use these 4 comprehensions at all. And I think that's a little bit what Golem has the potential to bring to us is solving this durability problem in a way where you get to write your code the way you want to. If you want to use Zio and you want to use 4 comprehensions, great. If you want to just write code in Rust, great. If you want to use Scala with just Caprese or with whatever, that's great too. You solve your problem the way you want to, and we'll add durability on top of that. I think WebAssembly is particularly promising for this because of that sandbox execution model and that polyglot language support. And I think maybe that's also pointing us towards a direction for the future where we may be a little bit less focused on the particular language. If you think historically, right, why did a lot of people get involved with Scala? Well, it was what Spark was written in, right? And that made a big difference because if you wanted the full API and the best API, you wanted to be kind of using the particular language that had that. Or maybe if we were in the Zio Flow world, right? If that was a great solution, you'd want to use Scala because you could use that thing. And I think a little bit of what WebAssembly has the potential to bring to us is these things being more accessible, where you have things like Golem where you say, look, if you want this functionality, you can call it from whatever language you want to, as long as there's a WebAssembly binding for it. And we can kind of put together these pieces in a more organic way that maybe makes it more open for all of us as developers to kind of use the tools we want to and pull those in. And also, if we develop something cool, make it available to the broadest audience possible versus kind of having to say, well, I'm writing this in Scala 3, and so I know there's only some small subset of people who can actually use this thing and having to kind of navigate that in your head. And that's what I've got for you today. So I want to thank all my colleagues at Zyverge, and in particular the Golem team. I've been really fortunate to work with a bunch of fantastic developers, and a lot of them are kind of the force behind everything that was cool and nothing that was not cool in what I showed you. So the functionality for going from Scala to WebAssembly, one of my colleagues, Jorge, who's going to be, I think, talking later today, worked on that. The front end is Nico here. Afzal and Peter did a lot of work on the API gateway. Daniel's done a ton of work on the core execution engine. So I'm very fortunate to work with very talented colleagues. And yeah, if anyone wants to build cool stuff, come join us at Zyverge. Also want to thank everyone who organized the conference, particularly Sandra and Agata for putting this together. It's been really fantastic. Also all of our sponsors made this possible. And then everyone I've had an opportunity to work with on Zio or any other open source work, either contributing or using it. And finally, all of you here today. So with that, I'd like to thank you all and hope you enjoy the rest of your conference. I definitely am going to enjoy having a chance to just watch the talks and not be preparing for mine as well. All right, thank you so much, everyone.